Hi guys, welcome to my channel. Myself Kaunavi. I am from Sri Venkateshwara College of Engineering in Bangalore. I am a student of Basic Science Department. My branch is CSC in AI. My subject is Mathematics 1 for CSC stream. Course code BMath S101. And my topic is Conduction of Heat. Introduction to heat conduction. Heat conduction is the transfer of thermal energy within materials. It occurs due to temperature gradients, moving heat from higher to lower temperatures. Understanding heat conduction is crucial in various engineering and physics applications. Alpha delta T plus QV by P to the PC base P is equals to dou T by dou T. Alpha is the material's thermal diffusivity. QV is the rate of which energy is generated per unit volume of the medium. P is the density, and so to the power base P is the specific heat capacity. Basics of heat transfer. There are three primary modes of heat transfer: conduction, convection, and radiation. Conduction is the primary mode in solids where particles are closely packed. It is governed by Fourier's law, which states that heat transfer rate is proportional to the temperature gradients. Mathematical modeling of heat conduction. The heat conduction process can be modeled using differential equation. A first order ordinary differential equation describes the temperature distribution over time. These equations are crucial for predicting how heat spreads in a material. Heat conduction equation: Q is equals to Ka, T to the base B is equals to T to the power base A divided by T. Q, heat flow rate. K, thermal conductivity. A, cross section area. Ta, high temperature region. Tb, low temperature region. D, thickness. Derivation of the heat equation. The heat equation can be derived from Fourier's law and the principle of conservation of energy. In one dimension, it can be expressed as dou T by dou T, that is equals to alpha dou square T by dou x square, where alpha is the thermal diffusivity. Simplifying this to a first order ODE requires specific assumptions and boundary conditions. First order ODEs in heat conduction. A first order ODE can describe the temperature change in a semi-infinity medium. The general form of the equation is dt by dt is equals to minus k, where T is the ambient temperature. This equation simplifies the analysis under steady state conditions. First order ordinary linear differential equation. Ordinary differential equation does not include partial derivatives. A linear first order equation is an equation that can be expressed in the form dy by dx plus p of xy is equals to q of x, where p and q are functions of x. Initial and boundary conditions. Solving the first order ODE requires proper initial and boundary conditions. Initial conditions define the temperature distribution at time T is equals to 0. Boundary conditions specify the behavior of the material at its edges or interfaces. For example, consider the system of differential equation dy by dt is equals to x plus 2y, dy by dt is equals to 3x plus 2y, with x of 0 is equals to 6, y of x is equals to 4. The solution is x of t is equals to 4 e to the power 4t plus 2 e to the power minus 1. Y of t is equals to 6 e to the power 4t minus 2 e to the power minus 1. Separation of variables method. The separation of variables is a common technique to solve first order ODEs. This method involves expressing the variables in a separable form to integrate. It helps in isolating the temperature function from time and separatal variables. Partial differential equation method of separation of variables. 4 dou u by dou x plus dou u by dou y is equals to 3u. Example problem setup. Consider a rod with one end held at a constant temperature while the other end is insulated. The first order ODE governing this scenario can be formulated using boundary conditions. This situation allows us to analyze transient heat conduction in one dimension. Steady state versus transient conduction. Steady state conduction occurs when temperature distribution no longer changes over time. Transient conduction involves time dependent changes as heat transfers through the material. The characteristics of ODEs differ significantly between these two conduction types. Graphical representation of solutions. Graphs can illustrate temperature distribution as a function of time and space. These visual representations help in understanding the heat conduction process. They can show the approach to steady state conditions over time. Applications in engineering. Heat conduction principles are essential in designing thermal systems in engineering. Applications include insulation materials, heat exchangers, and electronic component cooling. Engineers use first order ODE models to optimize thermal performances. Numerical methods for solving ODEs. Numerical methods such as the finite differences method can solve complex heat conduction problems. These methods approximate the solution of ODEs when analytical solutions are impractical. Numerical simulation provide detailed insights into transient heat conduction scenarios. Limitations of first order models. First order models simplify complex heat conduction phenomena but may overlook details in homogeneous materials or multi-dimensional problems often require higher order models. Understanding these limitations is vital for accurate thermal analysis. Alpha delta T plus QV by PC base P is equals to dou T by dou T, where alpha is the material thermal diffusivity and then QV energy is the generated per unit volume of the medium. P is the density. C to the base P is the specific heat capacity. Advanced topics in heat conduction. Advanced studies may involve nonlinear heat conduction equations. Multidimensional heat conduction and phase change problems are also critical areas. Researchers are exploring new materials with unique thermal properties for better performances. Summary of key points. Understanding first order ODEs in heat conduction help predict temperature changes. Proper application of boundary and initial conditions in crucial for accurate modeling. Analytical and numerical methods are essential tools in solving heat conduction problems. Heat equation transient solution. Dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Q by K is equals to PCP by K dou T by dou T. Future directions in heat conduction studies. Future research will likely focus on smart materials and adaptive thermal systems. The integration of computational methods with experimental validation will be key. Ongoing advancement in nanotechnology may lead to revolutionary thermal applications. Conclusion. First order ordinary differential equation are fundamental in heat conduction analysis. They enable engineers and scientists to model and predict thermal behavior effectively. Continued research and evaluation will further enhance our understanding of heat conduction. Solving first order linear differential equation. General, a first order linear differential equation as the form dy by dx plus p of xy is equals to q of x, where p of x and q of x are function of x. Dy by dx plus p of xy is equals to q of x. We multiply throughout by another function of x, I of x dy by dx plus I of x. P of xy is equals to I of x q of x. We choose I of x so that I of x dy by dx plus I of x p of xy is equals to d by dx of I of xy. This is because d by dx I of xy is equals to I of x dy by dx plus y di by dx. Thank you. Please like, subscribe, share my video.